Hello everyone. Today we will be concluding our discussion of street routing problems with a discussion of Eulerization and semi-Eulerization of graphs. Now, when we have a street routing problem, such as trying to figure out a mail route, trying to figure out a garbage truck route, or routes for a police car maybe, or whatever your application is, you may not always be fortunate enough to have a scenario where an Euler path or circuit is possible. So one way that we can sort of work around this is with Eulerization and semi-Eulerization of graphs. The idea behind both of these being that we are adding duplicate edges to a graph to make an Euler path or circuit possible. Now, when we're doing this, we want to try to add as few new edges as possible to try to keep our route as efficient as we can, and we cannot add edges where edges do not already exist. So let's look at an example. So over here on the right side of the board, we have a graph where we have 4 odd vertices, A, B, D, and F. This graph has too many odd vertices for us to have either an Euler path or an Euler circuit. So let's say we want to make this graph or adjust this graph so that an Euler circuit is possible. We would call this Eulerization of a graph. We are adding duplicate edges to make an Euler circuit possible. So things that we cannot do. We could not add an edge from, say, B to D, for instance, because that would be adding an edge where an edge does not already exist. This is not allowed when we are Eulerizing or semi-Eulerizing a graph. However, we can add a duplicate edge, for instance, from A to B. What that's going to do, we are adding a duplicate edge where there is already an edge. A and B are already connected. We're just adding a second edge connecting those 2 vertices. And now that we've done this, notice the degree of A instead of 1 is now 2, and the degree of B rather than 3 is now 4. So what we've effectively done is we've taken 2 odd vertices and we've added an edge to make them both into even vertices. We can do the same thing over here going between D and F. If we add a duplicate edge here, the degrees of both of these vertices are now 4. So we would say that this is a semi-Eulerization, or sorry, an Eulerization of the graph. When we are Eulerizing a graph, we are taking something that does not have an Euler circuit and making it so that it can have Euler circuits. So at this point, we've converted all of the vertices to even vertices. Therefore, an Euler circuit is now possible. We have Eulerized this graph. Related to Eulerization is what we call semi-Eulerization, and this is where we are adding duplicate edges until an Euler path is possible. So for an Euler path to be possible, we have to have exactly 2 odd vertices. So this graph over here on the left represents the Königsberg bridges problem that we introduced in the first video in this set, and I've written the degrees next to all of the vertices. So notice that all 4 of our vertices here are odd vertices. So this is too many odd vertices, once again, for us to have either an Euler circuit or an Euler path, which is why it's impossible to find a route that crosses all of the bridges in this problem exactly once. So if we wanted to find a semi-Eulerization of this graph to make an Euler path possible, we would need to basically just take 2 of these odd vertices and convert them to even vertices. That would leave us with 2 odd vertices remaining. So one simple way that we can do this is we just add an edge between A and D. This makes our vertex A degree 4, and for D, we now have a degree of 6. So we have exactly 2 odd vertices remaining, B and C. Therefore, we now have an Euler path possible, meaning that we have semi-Eulerized this graph. Thank you for watching, and as always, I'm happy to help with any questions that you may have.